This is Mboa Joseph presenting number 2, part B, about Wronskian. And Wronskian is a mathematical determinant whose first row consists of n functions of x and whose following rows consist of successive derivatives of those same functions with respect to x. In other words, if the determinant of the matrix constructed, it is the determinant of the matrix constructed by placing the functions in the first row, and then you press the first derivative of each function in the second row, and you go on until you come to the last derivative, maybe n minus 1, and you end up forming a square matrix. A square matrix is a matrix with the same number of rows and columns, that, for example, 2 by 2, 3 by 3, 4 by 4. Those are examples of square matrix. Now, from our question, we are given the Wronskian of smooth functions f of x, g of x, h of x is defined as the determinant. We have the first row for the functions f of x, g of x, and h of x. Now the second row is for the first derivative of those functions, and the third row is for the second derivative. And this definition can go on depending on the number of functions you might be interested in. Maybe there are 4 functions you are interested in, or 5 functions, but you realize this is a 3 by 3, it's a square matrix. Now the question is saying calculate the Wronskian of the polynomial functions 1 plus x, 1 plus x raised to the power of 2, 1 plus x raised to the power of 2. So we are going to begin by letting the first 1 plus x to be our function f of x, and then 1 plus x raised to the power of 2 to be our g of x, and then 1 plus x raised to the power of 2 to be our h of x. Now we need to get the first derivative for f of x, for g of x, and h of x, and it's going to be that first derivative. Then we also need the second derivative for that same function of those same functions of ours, and those are going to be the second derivatives for the f of x, g of x, and h of x respectively. But remember, from the definition of Wronskian, we have the first row for the functions, the second row for the first derivative, the third row is for the second derivative. So we substitute in and we shall get that. Now we need a workout for this. Remember, from our substitution, that's what we got. Now we need to get the determinant. Now the determinant of a 3 by 3 matrix, how do we do that? We are going to pick we are picking the first element, which is 1 plus x. Now when you are picking 1 plus x and you're at that row, the 1 plus x raised to the power of 2 and 1 plus x raised to the power of 2, they will become 0 on that row, and that still at the same element 1 plus x, 1 and 0, they will become 0, and you remain with the 2x and 2, and then you remain with 1 plus 2x and 2. Then similarly, the same idea is going to be applied when I'm picking 1 plus x raised to the power of 2. I'll apply the same idea, and likewise also when you're at 1 plus x raised to the power of 2, you remain with 1, 0, 2x and 2. But why are we having here a minus sign at the second element of 1 plus x raised to the power of 2? According to the rules of getting determinant, the first column, if you are using the idea of determinant, applying determinants, that will be for positive, then that one will be for negative. Then when you come to the next one, 1 plus x raised to the power of 2, that one will be a positive. In the case I had another element, in other words, if this was a 4 by 4, then the next one was supposed to be a negative, but here we are talking about a 3 by 3 matrix. You realize that I'm forming here determinants of 2, a 2 by 2 matrix, determinants of 2 by 2 matrix, which is easier to get because I remain with 1 plus x. Then I'll get a determinant of a 2 by 2, and you look at the major diagonal. You multiply the elements in the major diagonal, then you subtract the elements in the product of the minor diagonal. So I have 2x times a 2, then a minus 2 times 1 plus 2x. So the same idea will be applied to the next term and also the third term. So if you try to follow that algebra, you'll end up simplifying, and it will give you this screw, whereby some terms are going to cancel out. The 2x I will cancel out with the true x, the other is a negative, it's a positive. Minus 2 will cancel out with the other 2, and then minus 2x raised to the power of 2 will cancel out with positive 2 x raised to the power of 2, and you'll end up getting your Wronskian as a negative 2. But we need to understand the answer we are getting for Wronskian. What is the implication if we are getting a negative 2? Remember, the Wronskian is very important to us. It is very, very important. Remember, we are talking about thinking of these functions. We are thinking of these functions, differentiable functions, f of x, g of x, h of x, as being vectors in the vector space of a differentiable functions, and therefore we are looking at the uses of Wronskian. It is used in the study of differential equations, where it can sometimes help us show the linear independence in a set of solutions. When we talk about this, we need to understand fully. In other words, we are saying it is used in solving non-homogeneous differential equations, or it is used in solving systems of differential equations, and it will also provide us with information about whether or not functions are linearly independent or dependent. Therefore, what is the implication if we are getting our answer as a negative 2? We need to look at these ideas of linear combinations. So, from our idea of linear combination, a linear combination of vectors v1, v2 up to vn with the coefficient a1, a2 up to an is a vector. A1 times v1 plus a2 times v2 plus, until you come to the last combination, an times vn. So that's what we mean by a linear combination. Now there's something which is important about the coefficient when you are going to form what we call the linear combination. Now the linear combination, which we have got a1 v1 plus a2 v2 plus plus until you come to the last term, an times vn, are called trivial if all the coefficients a1, a2 up to an are 0. It is the linear combination which is going to be trivial if the coefficients are equaling to 0. That means that a1 equals to a2 equals to a3 equals to the last term, which is an, will be equal to 0. But a linear combination is going to be called non-trivial if at least one of the coefficients a1, a2 up to an is not 0. In other words, I'm saying you may have a1 not being equal to 0, but the rest are equal to 0. A2 is equal to 0, A3 is equal to 0, up to AN is equal to 0. But A1 is not. Or you might have A1 is not equal to 0. Maybe A1 is equal to P and A2 is equal to Q, but Q should not be equal to 0. And then the rest, A3 up to AN, is equal to 0. So at least one of the coefficient is not 0. Then we shall have a linear combination being called non-trivial. Now, this leads us to another idea which is important. The vectors v1, v2, and up to vn are called linearly independent if there are no non-trivial combinations of these vectors equal to 0 vector. In other words, if there are no non-trivial combinations, or you are saying if there are trivial, if there are trivial combination of these vectors equaling to 0, then you are going to say that these the vectors v1, v2 up to vn are linearly independent. What are we trying to mean? We are saying that vectors v1 and v2 up to vn are linearly independent if the combination a1 times v1 plus a2 times v2 plus up to the last term an times vn is equaling to 0. And that is true if and only if the coefficients are trivial. That means that a1 equals to 0, a2 equals to 0, up the last coefficient an must be equal to 0 for us to have what we call linearly independent. Now when we go back to our answer of Wronskian, we got Wronskian being a -2. What is the implication? So since the determinant is not equal to 0, in other words, you have got a -2. Since the determinant is a -2, means it's not equaling to 0, then the functions are linearly independent. F of x, g of x, and h of x are linearly independent because its determinant was not equaling to 0. But if it was equaling to 0, then it was going to be dependent. Thank you for listening.